Good day, dear colleagues, and hello to everyone who have joined us online. Today we will be talking about how distortion from massive MIMO base stations with nonlinear hardware is radiated in space. My name is Kristoffer Molén and I'm from Linköping University. And this work is a collaboration together with Ulf Gustafsson from Ericsson, Thomas Eriksson from Chalmers, and Erik G. Larsson from Linköping University. In this tutorial, we will introduce nonlinearities and show how they affect passband signals and what kind of distortion that they create. And then we will derive the radiation pattern of the distortion in terms of the radiation pattern of the in-band signal. And this is sort of shown in this figure here, where the red curve shows the radiation pattern of the distortion and the blue curve shows the radiation pattern of the input signal. So, what are nonlinearities and why are they interesting to study? An example of a nonlinearity in a radio base station would be an amplifier. And these nonlinearities, what they do is that they cause distortion, two types of distortion. One kind that we label in-band distortion. And this kind of distortion harms our own system and the performance of the users that we serve. And the other type of distortion we label out-of-band radiation, because it is the distortion that is created outside the allocated frequency band that we are using. And in the downlink, the out-of-band radiation harms other wireless systems that operate in the vicinity of our base station. And in the uplink, other systems in the vicinity in adjacent frequency band might leak into our own system and harm our performance. So what is the difference between distortion in a traditional single antenna system and in a MIMO system? Well, in a MIMO system, signals are beamformed. And this is actually the whole purpose of using multiple antennas, or one of the purposes. But what if the distortion is beamformed and focused to different spots in the area around the base station? Well, then it can be harmful to add more antennas if we concentrate the distortion, for example, towards a victim. So that is why we will analyze the radiation pattern of the distortion. Now, a typical nonlinearity in the systems that we are interested in can be pictured like this. Here is the output from a nonlinearity as a function of the input amplitude. And we can see that for small amplitudes, the output is almost a linear function of the input. But then at higher amplitudes, the output saturates, and we get this nonlinear region. Any transfer function like this can be arbitrarily well approximated by a polynomial like this, or at least in a mean square error sense. That is, if we replace the actual transfer function with a polynomial of sufficiently high order, then the mean square error can be made arbitrarily small. And for the experts among us, the Weierstrass approximation theorem might come into mind. So what we will do is we will analyze the nonlinearity using a polynomial like this. So how do these nonlinearities affect passband signals? What if the input signal to the nonlinearity is a passband signal like this? Here I used sans serif font to denote a baseband signal, a complex baseband signal, and normal Roman font to denote the passband signal. So the passband signal is given as the real part of the baseband signal multiplied with a carrier like this. And the real part, as you know, can be written as the complex signal plus its conjugate like this. Now if we input this to a nonlinearity, then the different terms in this sum will be given by the binomial theorem. So imagine that we input this signal in here. Then the first term will of course be the input signal. the desired signal. The second term will be given by the second row here in Pascal's triangle as these three terms. And the third term will be this, and the fourth term like this, and so on. And what we can see here is that all the complex terms here, they show up as conjugated pairs, like this. So we can use the real operator to rewrite these equations like this. And now it becomes clear that the output of the nonlinearity will consist of many different passband signals. But only a few of them, these two in this example, will lie on the carrier frequency. All the other signals here, and here, they will lie around multiples of the carrier frequency. And this can be better illustrated in a plot of the Fourier transform of the signal. So if this is the input signal, it's a passband signal located around the carrier frequency omega c, then the output will look something like this. It will consist of many different disjoint spectral components. And this becomes clear if we look at each term in the Fourier transform one by one. The first term is the input signal. The second term, the square of the input signal, will be a convolution in the frequency domain of this with itself. So it will consist of three terms located around the 2 times the carrier frequency and at the DC level. The third term will look like this. It will be the convolution between this and this signal. And the fourth term will look like this. And now we can observe that if we are only interested in the signal around the carrier frequency, then only odd degrees will matter in the polynomial. Even terms will only give rise to components around multiples of the carrier frequency. So again, this is the output of the nonlinearity that we are studying. And we usually label this part around the original carrier frequency as the fundamental, and all the other higher order terms as harmonics. And if the carrier frequency is big, which it usually is in a communication system, then these harmonics are fairly easy to filter out using a filter of fairly low degree. So usually we are only interested in how the fundamental is affected by the nonlinearity. So what we will do is we will study this fundamental closer. And as you remember, this fundamental is a function of only a few of the terms in the polynomial. So we can simplify or rewrite the polynomial from the previous slides into a complex baseband representation like this. And this representation is usually called the polynomial model. And it describes the baseband representation of the fundamental in the output. So given a baseband representation of the input signal like this, then the baseband representation of the fundamental is given as a linear combination of these complex polynomials, as we would call them. And the coefficients here are just rescaled coefficients of the old polynomial, the real polynomial. So how is the signal radiated in space? How do we determine the radiation pattern of a signal? Well, in order to do that, we need to know the cross correlation of the signal across the different antennas and its cross spectrum, which is the Fourier transform of the cross correlation. If we have this thing for all m and m prime, then we can compute the received power at any point in space to which we know the frequency response as this double sum. For example, if we have a uniform linear array and we are located in the far field, then the impulse response or the frequency response of a position located at x will be given as this. It's a function of the angle of departure towards that location. Beta here is a path loss, delta is the spacing between the antennas, m is the index of the antenna, and c is the light, the speed of light. So the answer to this question is given by this spectrum here. So if we can determine this cross spectrum, then we can also characterize the radiation spectrum of any signal. So that's what we will be doing in the next few slides. So we will rephrase the polynomial model in order to do this in terms of the Ito-Hermite polynomials, the first of which are given by these expressions. As you can see, the Ito-Hermite polynomials are linear combinations of our complex polynomials. So we can rewrite this characterization of the nonlinearity in terms of these Ito-Hermite polynomials. And why would we like to do that? Well, the Ito-Hermite polynomials are orthogonal. They are orthogonal in the sense that if the two arguments here to the Ito-Hermite polynomials are complex normal, circularly symmetric, and jointly Gaussian, then this correlation between two different Ito-Hermite polynomials would be zero if the degree of the two polynomials are different. And it would be some function of the input correlation when the degree is the same. So what we will do is we will assume that the transmit signal xm of t is a complex circularly symmetric Gaussian. And this is a good assumption if we are dealing with OFDM symbols or with pre-coded signals. If the signal is not Gaussian, then we would have to use some other kind of polynomial. But we will stick to complex Gaussian and the Ito-Hermite polynomials here. And now with the Ito-Hermite polynomial representation of the nonlinearity, we can do two things. The first thing is that we can split the output of the nonlinearity up into two terms. Remember that the first Ito-Hermite polynomial was just the input signal. That's the first term here. That we will denote as the decide signal. The other terms, which are orthogonal or which are uncorrelated to this decide signal, are all the higher order terms in the polynomial model. These terms we will denote as the distortion. And they will be uncorrelated to the decide signal because of the property the Ito-Hermite polynomials have. So now that we have defined what we mean by distortion, we can also derive the cross correlation of the signal. So we have an array of transmit signals that all are fed to different nonlinearities, and the output signals are given by y1 through ym. Then the cross correlation of these signals are given by this expectation. If we now replace this ym of t with the Ito-Hermite representation of that signal, then we will see that this expectation turns out to be a double sum of a lot of cross terms. Because of the property that the Ito-Hermite polynomials have, most of these cross terms, all the off-diagonal terms, will be zero. There will be just a single sum left. And if we write the single sum out, it will look like this. The first term will be the cross correlation of the decide signal. And the second part here will be the cross correlation of the distortion. Now if we are interested in the cross spectrum, what we do is we transform this. So the linear term becomes this and the distortion becomes that. And we can see that the spectrum consists of many different spectra. The linear one is of course the same as the input spectrum. And then different orders, different degrees here will result in different steps like this in the output spectrum. So the total output spectrum will be the sum of these spectra. So now that we have characterized the output from the cross spectrum of the output signal from the array, we can analyze the radiation pattern in any setting. So this analysis is fairly general and can be applied to any channel model. But to give some illustrative examples, we will look at a line of sight channel where all the amplifiers have the same linearity characteristics. That means that these Hermite coefficients are the same for all antennas. And we will look at 3 different examples. The 2 first will be looking at the in-band distortion, and the last example will be studying the out-of-band radiation. And the first example will be when we beamform towards one user, and then we will look at the case where we beamform towards multiple users. Let's start with the first one. Let's imagine that we have a uniform linear array like this with antenna spacing delta. Then if we want to beamform towards a user that is located at an angle theta, then we would like to select the transmit signal as this, if we want to beamform this symbol S towards this user. And as the experts among us know, this user has to be in the far field in order for this model to be accurate, and that means the distance to the user has to be greater than the Fraunhofer distance. But imagine that the user is in the far field, then the cross correlation of the transmit signals will be given by this complex exponential if the symbol is complex normal distributed. The cross correlation of the distortion, on the other hand, will be given by this thing that we derived in a few slides ago. And if we input the cross correlation of the input signal, then we get this thing here. And we see that the cross correlation of the distortion is the same as the cross correlation of the decide signal, except for this scaling factor, D. This means that the distortion will be beamformed in the same way as the decide signal will. And this becomes clear if we look at the received distortion at the angle given by the phase phi, like this. Then in this direction, the received power, or the received cross correlation, will be equal to this thing here, D times some array gain. And the array gain is shown in this figure here. So the user is located at this phi. So when this argument is 0, the distortion has the highest array gain, m squared, which is the same as the array gain of the in-band signal. And in all other directions, the distortion is radiated with a very small array gain. So the conclusions we can draw from this example is that when we have one beamforming direction in line of sight, the distortion is focused towards the served user, and in that direction the distortion has the same array gain as the decide signal. So the amount of distortion that the user receives will be the same independently of how many antennas we have. And in the regime of a very large number of antennas, then the signal quality, as quantified by the signal to interference, noise, and distortion ratio, will saturate towards this 1 over D. And so will the performance. Now let's look on the second example, where we have multiple beamforming directions. Imagine that we have now 2 users at different angles, and that we use maximum ratio precoding to transmit 2 different symbols to these users. Then the transmit signal at antenna M will be given by this expression here. And again, we will assume that the symbols to user 1 and user 2 are complex normal, circularly symmetric, random variables with different powers. And in this case, the distortion, the autocorrelation or the cross-correlation of this distortion will be given by this expression here. The distortion in the direction given by the phase phi. We can see that the distortion consists of 4 different terms. Each term consists of a power scaling and this array gain function. And this array gain function has its maximum when the argument is 0. So in the directions given by phi 1, phi 2, 2 times phi 1 minus phi 2, and 2 times phi 2 minus phi 1, we will have distortion beams. And this can also be seen in this radiation pattern down here, where we have 4 different beams in exactly those directions that I just mentioned. And these beams, they are scaled by some function of the input powers. And take the beam towards user 1, for example, then this beam is scaled by the third power of P1 and the second power of P2. And if there were an unbalance between P1 and P2, if we have done power allocation in such a way that P1 is much smaller than P2, then this power scaling matters. Let me show how the radiation patterns change when we change the power allocation between user 1 and user 2. We see that when P2 is much bigger than P1, then this radiation pattern is very similar to the case where we only have one beamforming direction. And what is interesting to note here is that the power in the direction given by phi 1, the direction of user 1, the distortion scales not with P2 cubed, as in the case of small MIMO systems, but as P2 squared, at least as long as we can neglect all these other terms, which we can if we have a massive MIMO system with many antennas. So the distortion in this direction, when P2 is much bigger than P1, is a little bit smaller in a massive MIMO system than in a small MIMO system. So the distortion is beamformed in massive MIMO, and it will limit the signal to distortion ratio. And down here I will show a sequence of different radiation patterns with different number of users. Here is with one user, and we can see that the signal to distortion ratio is about 33 dB. The difference between the desired signal, the received power of the desired signal, and the received power of the distortion is 33 dB. Then when we increase the number of users, the radiation patterns change, and so does the signal to distortion ratio. When we have 2 users, the signal to distortion ratio improves. It's now 35 dB. And this continues when we continue to increase the number of users. And we can see that the signal to distortion ratio increases until the distortion becomes isotropic, or approximately isotropic. And this happens when the number of users grows large in comparison to the number of antennas. If you plot this in a diagram like this, with the number of beamforming directions on the horizontal axis and the SDR on the vertical axis, we can see that the signal quality improves until it saturates at a large number of beamforming directions. And since the array gain of the distortion scales in the same way as the array gain of this desired signal, increasing the number of antennas does not improve the signal quality very much. In fact, it doesn't affect this SDR in any significant way. So, since the SDR limits the performance of the system, or the effective signal to interference, noise and distortion ratio, then the performance of the massive MIMO system will be limited by the nonlinearities in the system, at least if we don't do any proper distortion mitigation. And whether or not effective distortion mitigation can be done is still yet to be shown. Now let's look at the third example, where we will be looking at the out-of-band radiation. Up until now, we have been looking at the radiation pattern at frequencies inside the allocated band. What we see here is the power spectral density of the transmit signal at one of the antenna. The blue curve shows the decide signal, and it is band limited to about 0.6 in normalized frequency. It's a root raised cosine with roll-off factor 0.22. The red curve shows the power spectral density of the distortion. And as you can see, the distortion is not confined to the same band as our decide signal. It leaks outside the band. We have spectral regrowth. And now we will be looking at the radiation patterns at a frequency outside the allocated band, outside this decide signal, to see how the signal is radiated there. So before we have been looking at the in-band radiation pattern, now we will be looking at the out-of-band radiation pattern. So let's start with a case where we have one user. We are beamforming towards one user. The blue curve here shows the power of the in-band signal. The red curve shows the power of the out-of-band radiation. And these two curves should be compared to the radiation pattern of a single antenna system that has an antenna that is isotropic, omnidirectional antenna, that is serving its user with the same received power as our massive MIMO base station is. And this SISO system has the same ACLR as the transmit signals in our massive MIMO base station. Then the out-of-band radiation in the SISO system is radiated like this. And we can see that the out-of-band radiation towards the served user is almost the same as in the SISO system. So in that direction, there is no improvement by increasing the number of antennas. But in all other directions, there is hardly any out-of-band radiation at all. So in these directions, it improves a lot to use a massive MIMO base station as compared to a SISO system. Now what happens if we increase the number of users? Here we have 4 beam-forming directions, and all beams are beam-formed with the same strength in order to serve the 4 users with the same power as the SISO system is serving its user. And then we can see that the number of directions of the out-of-band radiation increases more than a factor 4. And since the out-of-band radiation is spread across more than 4 directions, the power of the distortion in the directions of the users, the power in the strongest directions, decreases. It's spread more evenly around the array. And this continues when we increase the number of antennas, and when we increase the number of served users, the number of beam-forming directions, until the distortion becomes almost isotropic. And also at this point, it is interesting to note that the out-of-band radiation is still significantly lower than in the SISO system. So the conclusions that we can draw from this talk is that with one beam-forming direction, the distortion is equally bad independently of the number of antennas in the direction of the served user. However, it improves significantly in all other directions. The distortion can limit the system performance when the number of antennas is really large, but this limit can be, in many setups, be very, very high. And when the number of beam-forming directions increases, then the distortion is spread over an even greater number of directions. And this spreading reduces the distortion in the strongest directions, and when the number of beam-forming directions is very big, then the distortion is almost isotropic. So hardware distortion never becomes worse when we increase the number of antennas. In most respects, it becomes better. And this talk is based on different publications. The first publication here is my PhD dissertation. The second publication, which has been accepted to the IEEE Communications magazine, is a paper that outlines the out-of-band radiation from large antenna arrays. The third publication is available on arXiv, and it describes all these mathematics that I have shown in this presentation. And in fact, all these tools that we have used now to analyze the downlink can also be used to analyze the uplink, and that's what's done in this paper that is also available on arXiv. So thanks for listening, and if you have any feedback or comments, please leave it in the comment section below. And please do subscribe to our YouTube channel.